This lecture is going to go over a different way to visualize numeric data. We already learned about visualizing numeric data through histograms and dot plots. Today, we'll learn about a different method called a box plot. And what a box plot does is it separates your data into 4 sections, where roughly 25% of your observations fall in each of those sections. In order to get that, box plots uses different types of medians. Now, what's really cool about box plots is they have a method to distinguish and identify outliers. We didn't really have or go over a concrete method with histograms or dot plots and how to identify outliers. We'll see the reason why box plots have a little advantage when it comes to something like this. So in order to create a box plot, what we're going to need is what's called the 5-number summary, or 5-num sum for short. And what it is it looks at the minimum value of your data set, the maximum value of your data set, and the median. Now those are the 3 measures that we already learned about. The 2 new measures that it uses are what's called the first quartile Q1 and the third quartile Q3. And to be honest, parts 2, 3, and 4 are all medians. The only difference is, well, what are you finding the median of? The third part of our 5-num summary is the median of your entire data set. The first quartile, Q1, is the median of the bottom half of your data, and the third quartile, or Q3, is the median of the top half of your data. These 5 numbers are essentially all you need to construct a box plot. So let's look at a little example of this. So here's an example of the hourly salary for 10 college student summer jobs. And if we were trying to visualize this set of data using a box plot, the first thing we should do is look at the min and max of our data set. So we have our minimum value of 11 to start and our maximum value of 30. Now to find the median, if we remember, we can use that location formula. So I'll write MED location as n plus 1 over 2. So we have 10 observations in our data set. And so it says go to the 5.5 point. So we'd count 1, 2, 3, 4, 5.5. And our median is the average of those 2 numbers, which turns out to be 17. To find the remaining 2 numbers in our 5-num sum, we look at the bottom half of our data set and the top half of our data set. And we'll find the median of these 2 data sets. So the median location in this case would be 5 plus 1 over 2, which equals 3. So we go to the third observation in our bottom half, which is Q1, and the third observation in our top half, which is 20. And so what I'm going to do is I'm just going to place little dots where each one of our 5-numbered summaries fall on our number line below. So I'll place a dot at 11. I'll place a dot at 14. I'll place the median at 17. Q3 is 20. And the maximum value is 30. So now what we'll do is we're going to make little dashes through each one of these numbers. And we're going to connect the middle 3 dashes. Oops, sorry about that. We're going to connect the middle 3 dashes at the ends. And the outer dashes we're going to connect in the middle. So this is what our 5-number summary looks like, and how we can use it to construct a box plot. Now, something that may have crept into your head was, well, what if I have a data set, for instance, of, I don't know, 5 numbers? So I'll just write a random data set right here. Well, if we were to look at our median, we can probably tell our median is smack dab in the center. Well, if we were trying to find Q1 and Q3, the question is, Do we use our median for both sides, for one of the sides, or neither? Typically what you'll find is to find Q1 and Q3, you don't use the median twice. You would just use the other numbers outside of the median. And so this is how you would do that for a data set that the median was a single value as opposed to the average of the middle two values. So let's look at some of the elements of this box plot. Each little section is comprised of roughly 25% of observations. So all of these little sections are containing 25% of observations. What's nice about box plots is that it can create what we call the inter-quartile range. And what the inter-quartile range is it's a measure of spread. So I'll write a measure of spread. And it looks at the range of your quartiles. So instead of taking the max and the min, it looks at the range of the middle 50% of your data. So if we were to find the range of the middle 50% of your data, that range is the IQR, that distance. So in this case, our IQR is, we have Q3 of 20, we have a Q1 of 14, our IQR is 6. The middle 50% of our data spans 6 units. And what's nice about this measure of spread is that while it does only use one or two or a couple observations, it's not susceptible to outliers or skewness, right? We're only measuring the middle 50% of our observations. So if you have crazy outliers, if you have, skewed data, the IQR is going to kind of not take that into account. It essentially uses the middle 50% of your data as the crux, the foundation of your data set. So let's see how we can use this IQR to detect outliers, because that's what's really cool about box plots. So we're going to take Q3, and this may seem like a random formula to start, and we're going to add to our Q3 the quantity of the IQR times 1.5. Again, it seems maybe kind of random. And then what we'll also do is we'll take Q1 and we'll subtract the quantity of the IQR times 1.5. Now again, this may seem kind of like I'm pulling this out of a hat right now, but just stay with me a little bit. So in this case, right, what we have here, if we were to do this out mathematically, is we have the values, the Q3 is 20, and then we're going to add the quantity of 6 times 1.5. And if we were to do this out, we end up with 29. We'll do the same thing for Q1. We'll take Q1, which is 14, and we're going to subtract the quantity of 6 times 1.5. And if we were to do that, we get the value of 5. And so here's essentially what this is saying. I'm going to erase kind of this other stuff. What it's saying is how far away from the crux of your data, the foundation of your data, the middle 50%, how far away from the foundation of your data does an observation need to be for us to consider it to be an extreme distance away from our mean? Or excuse me, an extreme distance away from the foundation of our data. And these two formulas roughly give you that distance. These distances, I'm going to create little invisible fences. We call the top one the upper fence, and the bottom one the lower fence. Now you won't see these on a graph, but these are invisible fences. And any point beyond this fence, or our lower fence, we consider an outlier. Now, there's different types of outliers. So right now what we just did is we calculated what we'll call a mild outlier. So these are mild outliers. But some observations may be kind of far away from the foundation of your data, and other observations may be very far away from the majority of your data. So what we do is we say, well, okay, let's classify different types of outliers. The second type of classification that we have is what we'll call an extreme outlier. And the only difference between a mild and an extreme outlier is what we're multiplying this quantity by. So instead of 1.5, we're going to multiply this quantity by 3. So we're going to change these observations, or these quantities, to now be multiplied by 3. And if we were to do this out, we'd find we get two new fences. We'd get the value 38 and the value -4. So I'm going to create new fences over here and maybe over here. And any value beyond these red fences is what we will call extreme outliers, observations that are very far away from your data set. Anything in the blue kind of ranges that we see here, we will call mild outliers. So I'll write this as mild, I'll write this as mild, and everything else is extreme. Right? Extreme. And depending on the type of outlier or outliers you have, may affect on how you analyze the data. So it's very important to distinguish the difference between mild and extreme outliers. Now again, we didn't really see where that 1.5 and that 3 came from. Right now, these kind of just seem like mystery values. These 3 and the mild outlier calculation that used the 1.5. Statisticians have deemed these values to be close enough values to get a sense of observations that are far away from your set of your data. A little bit later in this course, when we gain some more knowledge about statistics and probability and things like that, we can talk about a little bit more why those values come into play. Right? They are nice whole numbers, 3 and 1.5, as opposed to 1.4 or 3.072, right? So there is just some kind of nice rounding to them. But they're not just randomly chosen out of a hat. Again, we'll see a little bit more of where they come from down the road. But what we have in a box plot now is when you have an observation that is an outlier, what you do is you alter your box plot for that. So what we'll do, and what you'll see on software and things like that, is a box plot will denote outliers. That value of 30 fell beyond our fence and into the mild outlier category. Maybe I should make that as a blue outlier just to kind of keep it consistent. So what we'll do next is we'll say, well, okay, this was deemed to be a mild outlier. We'll then go to the next observation in your data set, which in this case is 22. And if your next observation is an outlier, we would denote it as such. In this case, it does not fall beyond our fence. And so 22 will be our new quote-unquote max value. It's not the maximum value, but it's the maximum value that's not considered to be an outlier. This right here would be your complete box plot visualization. So what you would see kind of on software is you wouldn't kind of see any of these percentages or probabilities up here. You wouldn't see any of these invisible fences. So these fences wouldn't exist. Although they're being used, they don't show up. This is what your box plot would look like. Hopefully you have a better understanding of how we use box plots, how we use them to construct outliers and things like that. But they're a really nice, effective tool to visualize data a different way and to detect extreme observations.